It's got a total of 8 coulombs is coming outside of this thing. It's the charge, and there's an electric field. Now, which way is if I'm going to draw my electric field lines off this thing, which way should the arrow point? Towards it or away from it? Away from it. All right, so we're going to go ahead and have some electric field lines. Go like this. All right, now then, at a point out here, at a certain distance r from the center of this thing, certain distance r, there's an electric field that's going through there. And we can compute that by using the surface. We can find E times A equals the Q enclosed divided by that permittivity of free space. Boy, that's hard. Right? Here's what we're saying. We're saying that we've got E times A equals the Q enclosed, which, what's my Q enclosed again, real quick? 8 microcoulombs, or 8, the funny looking, the micron guy. 8 microcoulombs divided by E naught, and where A, we would say this would be a sphere, so it would be 4 pi r squared. All right, now, out at that point R, these 8 microcoulombs, this Q enclosed, actually has there's a potential. All right, and remember, we talk about potential difference, and here's the equation for it. EV, my voltage, V, is equal to my K times Q over R. Okay? All right, let's put the big R there so you don't get confused. KQ enclosed. Okay, so that's the Q enclosed again over R. Okay. Now, remember, we say we take a voltage difference. So the difference that we're doing is what if R is at infinity? What would be my voltage in that case? 0. So we take the V, that V minus the 0, and we get this guy. Yes?
Is that the on the bottom of enclosed?
The enclosed here? No, I'm just saying enclosed. Right here? Yes. That is your good old permittivity of free space. Okay? All right. Now, so that's what the book is trying to tell you. All right? Now then, the other thing the book, and that's a little bit later on. All right? So, if you have, and the other, we're going to go through we're going to go through the first half of the little clicker questions, and that'll take about 15 minutes or so once I get to it. And then we're going to do about 5 of your 12 homework problems from chapter 16. Because I was doing them, and those suckers are hard. I was like, oh man, I'm going to start being more selective how I pick them. Because, one, the geometry of them is kind of tricky when the E and M is hard enough. So it's like, wow, I don't really want to test them on their geometry skills, but you're kind of expected to know some geometry. But anyway, we'll get through that problem. Now, the other thing, the first thing that the book was trying to tell you was that the energy, okay, let's do this. All right, the energy, the electric potential energy of something, which they call U, is equal to Q times V. All right? So, that's what the electric potential energy is. So, these are the two, believe it or not, after all that confusing stuff that I threw at you on Wednesday, this is the only 2 things we learned. Okay? Was that at a certain distance out there's a potential, all right? And that the electric potential energy U is equal to the charge that we're trying to bring close to it times the voltage. So, now let's take a look at the computer here real quick. Let's not look at that yet. Not just yet. Okay, you can get a few of the answers. So the first answer is going to be E, it looks like. But we're not going to do that right now. I want to do this. I want to look at the charges and fields here real quick. Let's take a look at the chart. This is going to give us our voltage. Now, here we go. I'm going to put a positive charge here. Boing. Okay. And notice the voltage out here is 3.4. Let's go ahead and plot it. Bing. Okay, so the voltage out here is 3.4. Now, what's going to happen when I put this negative charge right here? What's going to happen to that potential line there, do you think? It's going to come way in. It's going to, okay, when I put this guy here, I'm going to put him back right now, so this line is probably going to go way inside here because that's a positive 3.4, and when I bring this guy here, boom. Ooh, I've got negative 1 out here now. Let's plot the voltage line of that. Let's plot what's going on right here. Okay, that one's still positive. That's 11.7. But somewhere between these two, charges, what is the potential? Zero. Somewhere there's going to be a zero potential there, okay, between these two. It's harder than heck to find it, but we can do it. Now, there's an electric field line. This gives me my E-field sensors. There's an electric field that's coming out from this guy, coming straight through this guy, all right? And to put a charge, let's say this distance, then I thought I had a tape measure. I guess not. Not in this one. I thought they gave me a tape measure so I could do the thing. All right, let's figure out what this one is. All right, so what we're going to be doing is we're going to see how much energy it takes to build a triangle of static charges. All right. And in fact, you've got 2 homework problems that are like that, so there better be a question like that on the test if I put you through the torture of doing those. All right, so let's go ahead and do a quick review of this thing. Let's go ahead and start here, slideshow, view show. So here we go. Get out a sheet of paper, get a blank sheet of paper out. There's probably going to be about 10 or 12 questions. It won't take all that long. Won't beat you up too much. Today, it's Friday. Darn it. We used to say in the Marine Corps, it's only 2 more work days till Monday. All right, so now, here we go. Change this. Okay, here we go. A proton. Now, ignore. I keep telling the company, you've got a 2Q here and it's confusing. All right? You've got a 2Q here that's confusing. The electron, the proton, they're saying a proton and an electron. Just a proton. All right? Not a 2Q. It's a 1Q here. All right? Okay. An electron are in a constant electric field created by oppositely charged plates. Okay, so this means that this E field is the same all the way across here. Okay, so the E field is the same all the way across. Now then, what we're going to do is you release the proton from the positive side. So we're going to release this proton from the positive side. What's it going to do? It's going to go, hey, I'm going to follow that E field, and I'm going to crash into that negative side right there. Okay? Got a question for you. Is the work that the E field does, is that positive or negative work done by the E field? Which way is you got to think about this. What is work? Do you remember from first semester? What is work? What's the easy definition of work? Force times distance times the cosine of the angle, right? So, in other words, if the distance is in the same direction as the force, if the displacement's in the same direction as the force, that is positive work, right? Right? In other words, the work done by gravity, here's what they're basically asking. If I drop this, the work done by gravity is going to be positive, right? But the work done by me is also positive, lifting it up here, but the work done by gravity that's opposing it would be negative, so that the total work, the total energy would equal 0. But anyway, so is this energy as it goes flying over here? So now, with that in mind, which way is the force acting on that proton going? Is it going to the right? Yes. Is the proton going to the right? So is the energy positive or negative? Positive. That wasn't the question. But anyway, now then, the electron. The work that now this is what kind of gets into people's brain housing group a little bit and kind of messes them up, is that you've got this electron over here on this negative plate, don't we? Please have the electron on the negative plate. Yes. And the electron from the negative side. Okay, so the electron's going to be over here, and it's going to go whoosh. Now, just because the E field is pointing this way, which way is the force on the electron going? To the left or to the right? To the left. Which way is it displacing? To the left or to the right? So the energy done by the E field would be what? Positive. Because the force times distance is negative times negative is positive, okay? All right, so keeping that in mind, that's a tricky thing to do, and that's one of your homework questions, one of your multiple choices, so at least if you get it wrong, you can pick the other one, all right? But anyway, all right, so anyway, here's a question. A proton and electron, they're both released. Which feels the larger electrical force? What does electric force equal, again? You got that big fancy Coulomb's law, but we also know about the electric force. The other one about the force is equal to the charge times the E field. Okay? All right, it's the charge times the E field. Is the E field the same for both of them? Is the electric field the same for both of these guys? Yeah, it's the same electric field, just like gravity. It's the same electric field between those two plates. Are their charges the same magnitude-wise? But they're opposite in sign. The charges are opposite sign. So which is our correct answer? E. They feel the same magnitude of force, but the forces are in opposite directions. I think that'll be right. Boom. Okay, since F, this is a good equation. F equals Q times E. Yes, Sarah? No, it's not.
What is the Q and the 2Q? What do they have to do with the problem? Does that have to do with like the force or something?
Exactly. That's not a dumb question. That's what I'm saying. This thing is written badly. They should have a positive Q here and a negative Q here, just for the charge of the electron and the charge of the proton.
So the proton isn't feeling twice the amount of...
No.
Oh, okay.
They made a mistake.
Okay.
But it's still a great question, but it's a bad picture, and I can't fix it.
Okay.
Okay? All right. So that's a good question. It wasn't a stupid question. Because if this is 2Q, it's going to feel twice the force. You're absolutely right. It'll feel twice the force. Okay. So, right. Yeah. Yes. Okay. All right. Now, a proton, now, again, positive 1Q. I can't get rid of it. Positive 1Q, negative 1Q. By the way, what is Q real quick? You should know this so you can win a bar bet sometime. Somebody asks you, well, what's the charge on an electron? What? 1.6 times 10 to the what? Negative 19 coulombs. Okay? All right? What's the mass of an electron? Mass. Yeah, dinky. 9.11. Yes, times 10 to the negative 31. What is the mass of a proton? A little bit, a lot bigger, like 10,000 times bigger. 1.67, I think, times 10 to the negative 27. Yes. Whew. Kilograms. All right. What's Planck's constant? Kidding. All right, we'll learn that later. Okay, you all might know that because you guys are chemistry wizards. You might probably know that. Okay, all right, here's a question. This quiz might last the entire hour, but oh well. All right, a proton, but this is really important that you can understand this. So since we spent so much time on it, you might see this guy again for the test, okay? All right, so a proton, so those of you out in TV land, you might see this again. All right. A proton and an electron are in a constant electric field created by oppositely charged plates. Okay, yeah. We've done that. Okay, you release the proton from the positive side and the electron from the negative side. Which has the larger acceleration? That's why I went through that whole mass thing. Which one's going to have the larger acceleration? The what? It's going to be the same proton, electron. Whoa, Abigail, say that one more time.
Proton has more mass.
So therefore it has a wrong. F equals ma. So if m is, we already said that they experience the same force, right? So if F equals ma, and they're both the same, and one m is really small, then what's its A? Really big. Okay? So it's the electron, right? Should be the electron has a much greater acceleration. It's really moving. It's hauling. That's how we get electricity. Electrons moving. All right? In other words, here's the deal, as they say. Okay? Here's the deal. In other words, this is a battery. All right? This is a battery. Plus side, negative side. You get these electrons to move, that causes current. That makes the lights come on. That's our world. Okay? That's our world. And being able to figure out, you genius chemists figured out how to do batteries by studying chemicals and how their energy works and how they flow around, okay? And you set up this positive and negative side. So if I get a big positive and negative side on the terminal and I put a wire here, what do its electrons want to do? Move away, right? And if I connect the other end of the wire over here to the positive side, all right, so those positive things go away and they attract the electrons. So I get a current going. All right? That's the next chapter. But because of conservation of charge and everything, that's the whole story. That's E&M right there. We get electrons to move, and all the rest of it is how we control it inside a circuit. Okay, so it doesn't kill us. All right? So anyway, next question. This is going to be about energy. Remember, Q times V. Q times V equals the energy. So keep that in mind. Q times V equals the energy. So here we go. Okay, so we got the electron, right? All right. So now, a proton and an electron are blah, 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 yada, yada, yada. When it strikes, okay, so now we're going to release an electron. Whoosh, bang. Release a proton. Bang. What about their kinetic energies? When it strikes the opposite plate, which one has more kinetic energy? The proton, the electron, they both acquire the same Ke. They both acquire the same Ke, but with opposite signs. What's the deal here? What? Somebody said a tentative C. Does that make sense? Okay, Q times V. Q times V. Is the charge the same for both of them? And the voltage is the same. One's just going from negative to a positive, the other is positive to a negative. Oh, but do they acquire different signs? No. The QV equals KE. So I think the answer, if you said D, you're way behind. Yes, Richard, this will be scary, but go ahead.
Could it be that they have the same kinetic energy because they both experience the same change in potential energy?
Exactly. They both experience the same change in potential energy, so therefore they have the same kinetic energy. Great. Perfect. Because their potential energy at the end equals their kinetic energy, just like when we drop something. Okay? Just like when we drop something. All right. Now, what will be different will be their velocities. Will be much different. Because Ke, what does Ke equal again? Remember? 1/2 mv squared. So if you got one with a much bigger mass, it's going to be going a lot slower, but it's going to have the same energy. It's just like if you get hit with a bullet going almost the speed of light or an elephant, it's the same thing. Going 5 miles an hour feels the same. Okay? Kind of. Probably a little different, but same idea. In other words, but elephants and bullets are protons and electrons, really. Think about it. All right. Did I tell you about the mosquito in the stadium? Did I tell you that story? All right. Well, it's not really a story, but it's the way you can think about, and even in chemistry you can think about an atom. All right? The entire mass, in other words, if I think about Arrowhead Stadium, okay? Arrowhead Stadium is the area that my atom is taking up, say a hydrogen atom or whatever, okay? Now then, The entire mass of this area is contained in a mosquito at the 50-yard line. That's where my proton and neutron are. And the electron is way out everywhere else. Okay? So that's why in quantum mechanics, weird things happen at the subatomic level. Things can pass through things relatively easily because it's easy to get between that, the edge of the parking lot and that mosquito on the 50-yard line. There's a lot of room there on the subatomic level. All right. But anyway, okay. So, boom. Something to think about. All right. Anyway. Okay, let's keep going. This is so much fun. I'm having a ball. I don't know about you all. Okay. Uh-oh. Right, George. Here we go. This is the tricky stuff. All right. Now then, I haven't taught you this, so let's go learn this real quick before we get into it. All right. Here is how we do this, and this is like 2 of your homework problems, and both of your homework problems, I'll be honest, the 2 that are like this, I kept screwing them up and screwing them up and screwing them up, so we're going to do them together in class today. If it kills me, we're going to do them, because I finally got them right. All right, and I'm going to push you in the right direction. I'm going to come after you, dog, but ain't no. All right, so we're going to scrap. No, here we go. Now, here's what we're going to do. We're going to figure out what the entire energy is of a configuration. And here's how you do it. Let's take this one. Let's say it's negative 2 microcoulombs. That does no good whatsoever. Let's make this, here we go, negative 2 microcoulombs. There we go. And I'm going to bring in another. Now, when I first start out, these guys are at infinite distances away from each other. And at infinite distance, when we're talking about charges this big, could be a meter, as far as they're concerned, all right? And then, so when they're out at those infinite distances, the potentials that they have on each other are 0, and then we're going to bring them in, okay? And this one is, let's say this one is plus 2 microcoulombs, and then we're going to bring in a big kahuna over here of charge, and he's plus 5 microcoulombs. And they are all 0.15 meters apart. Okay? They're all 0.15 meters apart. Now, the question is this. How much energy did that take to build that? How much energy is there? How much energy is in this thing? How much energy is he putting out? Here's how you do it. The potential energy of this guy, we'll call him charge 1, 2, and 3. And so this would be line 1, 2. This would be line 2, 3. And this would be line 1, 3. Is equal to the U for 1 and 2 plus the U for 2 and 3 plus the U for 1 and 3. All right, where U is equal to, in general, Q times K, Q over R. Q times V. Well, this is my Q times V. All right, so now you got the picture. Let's do some calculating on this real quick. All right, so what we would do, so this is important that we go through this. So here's what we did, because this is you got a homework problem just like this. Then you got another one that's real annoying where it's on four corners. That was dirty pool. I put that one on there. But anyway, all right, so let's start with, first of all, the amount of energy to get this triangle around this guy was 0, because he's the first one I'm starting with. Okay, that's just going to be my 0. Okay, so he's 0. All right, so now U12, which is this one, is equal to, what's the charge of Q for this formula right here, for Q times KQ over R? For my U12, sorry, let me put that in. For U12, I'm bringing in the plus 5Q, 5, so it's going to be 5 microcoulombs times K times Q negative 2 microcoulombs over 0.15 meters. Okay, so here's my V times the charge of 2 that I'm bringing in here. In other words, what we're doing is we're finding the potential caused by Q1, this U12 stands for the potential of 1 multiplied by charge 2. That's what it means. Okay, and the potential, remember, is KQ over R. All right? And that looks like that's going to be 10. That's going to be negative 10 microcoulombs times K over 0.15. All right? So now let's find U23. Uh-oh, I didn't mean to make that as a microcoulomb guy, but I did. Sorry about that. He's not. This is U. This is. That's the one problem with this. Erasing. Let's do this. U23 then equals. Okay. So the potential caused by 2, this guy, multiplied by charge 3. That's what we're doing. Okay? So I'm going to take charge 3. He is positive 2 microcoulombs times the potential caused by 2, which would be K times 5 microcoulombs over 0.15 again. And so this comes out to be do it again. U23 is equal to 10 K, 10 microcoulombs times K over 0.15. So far, so good. Uh-oh. We got to add those two guys together. What do they come out to be? 0. Got that right. Little symmetry in here. These two and these two. They kind of cancel each other out, don't they? We got one left to do. What is it? These two. Can I go ahead and be so bold as to say this is going to be negative 4 microcoulombs K over 0.15? Do you see where we got that? Okay. And so U13 is going to equal negative 4 microcoulombs K over 0.15. I add all those together, and what do I get for my energy? Negative 4 microcoulombs K times 0.15. So this guy has, that's weird. Huh. That's kind of funny. We did it right. I know we did. I put it on my mama. We did it right. Now, hold on. Yes, this is negative 4. So negative. Okay. It just seems funny to me that because I've got positive, kind of Coulomb heavy there, and it winds up with a negative charge. But okay, with negative energy. All right, but that's what the math says. I'm going to believe the math. There we go. And so when I add all these up, so when I add up 2, 3, 1, 3, and 1, 2, I get a negative 10 plus positive 10 minus 4. So it comes out to be that U equals negative 4 microcoulombs times whatever K is going to be. Well, I know what K is. 9 times 10 to the 9th over 0.15 meters. Interesting. Okay. Now then. So let's go back. Let's go back. Computer. All right. Here we go. Which group of charges took more work to bring together? That's what we're looking at, that U of the work to bring those charges together. All right, which one of these looks like it's going to take more work to bring together? A, B, or C? A. You think? Think about it now. Uh-oh, now you're going to say, no, it's not A, it can't be A, because he's making us think about it. We get it right, he moves on. Now look, what's the potential that's being caused around this guy right here? What's his potential out at this point D? It is, his potential is 2 times K over D times 1, so it's 2 times K over D. This guy, we got to do this one. We start with this guy, and he's 1K over D, right? Yep. And this guy, we got to do this one, and then this one. So there's how many that I've got to do on that one? 3. How many was, so this is 3 energy units, and this one was 2. Right. Right. So the answer is B. I know this because I went through it first before I came in here so I wouldn't stumble over myself. Now watch, and they give a good explanation of it. Okay, so the potential energy here, remember I had my Q's out here on this side of K, but anyway, they go, remember the potential energy is K times Q1 times Q2 over R. And then you add it over all the pairs. Okay, so for this one I've got 2Q times 1Q over R, so that's 2QK over R. And this one, I've got to do it over all the pairs. So I've got KQ over R plus KQ over R plus KQ over R, so that's 3KQ over R. Okay, that's for case 1. And this is for case 2. Over D, whatever. D, R, whatever. It's all the same. It's all the same thing among friends. Okay. Let's look at one more question. Let's go look at your homework real quick. Do a couple of those problems. They're ugly. They're ugly. All right. Oh my. Here we go. What is the electric potential at A? Oh, they're just making us do, we just have to decide if it's greater than or less than 0 or equal to 0. All right, here we go. Looks like they've got, I got a real quick question for you. What's the electric potential at, oh, okay, well, we'll get to that in a minute. What's the electric potential at A? Is it going to be greater than 0 or less than 0, do you think? By the way, for those of you sitting on the sides or in the back, for Chasey and for the crowd over here, I got plus 50 and I got a negative 50 over here. All right? So, with plus 50, so this plus 50 and this negative 50, so this is going to be greater than or less than 0? Greater than. Because the plus 50 is closer. So that's greater than, right. And this guy is a lot further because I've got KQ over 30 plus negative, 50K over 30, and then I've got negative 50K over 60. So in other words, this is only half of what this is. So I've got, it's basically 25 microcoulombs times K over 30 is my thing, and that's positive. Now, what do you think the next question is going to be? About B, probably. Oh, good, it's positive. Whew! Because you just add them up. You just add up the potentials. The V caused by this guy and the V caused by this guy, where it's KQ over R. They're distance apart. Now, let's try this guy. Ooh, over B, what do you think it is? Just like that. 0. Let's see. If this is the same height, so this has got to be 30. So we've got 26, 30. Yep. So that's the same distance. That's the same distance. I love symmetry. I believe in symmetry. So let's say it's 0. You guys are geniuses. What is the potential at the origin of the XY axis? What's the potential right here? 0. What's the potential right here? Right here. All right, so we've got a question like that. I think the next one is like that. Oh, I don't want to do it anymore. I'm tired of this. All right, let's go ahead. What do we got? Oh, I forgot to load your homework. Here we go. Let's go to Mastery of Physics real quick. Now the capacitor stuff, I was hoping that we would just do nothing but capacitors on Monday, but it looks like we'll probably do homework and capacitors. We'll finish the chapter on Monday, but I wanted to make sure that you had a good foundation of this whole potential thing. All right, so here we go. This is me. Log in. Courses. Now I did it on the take on the video people, so I don't have all my wrong answers. All my bad attempts aren't here. All right. Here's your first question. It says 3-point charges, each with a charge of 1.75 microcoulombs, are placed at the vertices of an angle of a 0.6 meter equilateral triangle. What is the electric potential energy of the system? They wanted you to use E naught equals 8.85 times 10 to the negative 12. You can use K. Because what they're saying, this is really annoying what they did, what they want you to do. They want you to do it this way. And I don't want you to do it this way. They want you to say that V, have I showed up? Yeah, I've showed up. Okay. They want you to say this. They want you to say that V is equal to Q over 4 pi echo naught times R. Well, that's, no. We're going to take this guy, because 1 over, now this is a mistake that I made on Wednesday. 1 over echo, that equals K, which equals 9.00 times 10 to the 9th. Okay? All right, so use K. Don't use that. This is for if you're going to go on and take like physics 460 and stuff. And I don't know, but I wouldn't recommend it. All right, anyway, yeah. Especially if you're working on doing other things. All right, if you want to be a physics major, I'll be more than happy to talk to you. And hey, if I got through that class, anybody can. So here we go. Now, we got 1.75 microcoulombs. So you guys know how to do this. This is just like what we did earlier. Okay? This is just like what we did, except all the charges are the same this time. So this one should have a nice positive potential energy, right? So basically what you do is you set up your triangle, and remember that here's your, I'm going to jump back real quick. I've kind of liked this new dot cam method. I know it's probably, I don't know if it's too annoying. You're going to do the same thing. So you're going to put 1.75 here, 1.75 here, 1.75 here, and 0.6, 0.6, 0.6, and use 9 times 10 to the 9th. All right? And you'll be fine. You can do it. All right? So let's go to the next problem. All right, this one. Okay, oh, I also learned this. Watch this. This is too cool. There, now it all fits. I got it all to fit. Okay, now, this one is tricky, hard. As my Don Bosco students say, got me too heated. But anyway, when I was doing it. So, here's what we're doing. We've got to find out the work again. We've got to find the factor of this thing. So basically what you have to do is you got to go through the whole thing, except now that I have 4 charges, here's the problem. Here's the problem with it. And I'm going to give you what, and you're going to do all this work, and then the answer you're going to go, it's that? Yeah, it's that. But anyway, so now what do you think the answer is? Ha! Geniuses. Yes. Okay. But anyway, here's what happened. .chem. .chem. There it is. All right, now. So you got this, and this. So this is the negative, this is positive, this is positive, this is positive. This is L, this is L, this is L, this is L. But we also have two other things we've got to consider. What are they? The diagonals. Exactly. Genius. Very good. What is the diagonal? What's the distance between here and here? L square root of 2. Exactly. L square root of 2. So, and you also have this one. You also got to figure that one too. So basically what you have, if we remember these 1, 2, 3, 4, you've got to do the total charge then is U of 1, the potential of 1 times 2 plus the potential of 2 times 3 plus the potential of 3 times 4. That's going to be a negative one. That will cancel out this one. These two will cancel out probably. This. Yeah. And then plus, I'm still going here, 4 on 1, the potential of 4 on 1, plus the potential of 1 on 3, or the potential of 3 on 1, it doesn't matter, they're the same thing, plus the potential of 4 on 2. So we got 6 of them to add up. Hey, that was annoying. All right. Okay. So that's the way you go about doing that problem. It was entertaining. People in the physics department were learning new words while I was trying to do it. Okay, so y'all have already figured out that's the bonus for coming today. Besides, oh yeah, I gave you that quiz too. What time is it? Oh, we're running out of time. Well, just when we were starting to have fun. All right, now. Okay, now we go to part B. Let's go to part B. Which one of these, and then I've got one more problem I want to show you real quick, show you how to do it because they did you dirty. They gave you something like this. You got to find the chart. You got to find the potential in the middle of a isosceles of a equilateral. Thank you. Better know I taught math, would you? Equilateral triangle. All right, now. So in this one, which one of the following figures depicts a charge configuration that requires less work to assemble than the configuration of the problem introduction? The problem introduction required how much work? 0. Required 0 work. This one will require, so this one, which one do you think? Well, this is the same one. This is the same thing. It's just 2L or L doesn't make any difference. So this one's 0. B? You think it's B? Because we got to figure out, we got to do this one. This would be times 2L. And then this one kind of wipes out. This would be KQ over L plus 2Q over 2L plus times 3Q over, oh, this one over 3L. Yeah, it's A. Because, I'll tell you why. When you try and scrunch things together, especially like charges, if you try and take a handful of positive charges here and a handful of positive charges here, and then you play with magnets, where you got the two north poles coming together, what happens? They go like this. It's hard to get them together. The bigger the magnets, it's almost impossible to get them together. Same thing's going on here. We're trying to scrunch these little charges together here. All right? We're trying to get everything scrunched. So I think it's A. Let's just take a guess. A. Yes. That's good. I did it before it came. All right. All right, now. Last thing. you're going to get a problem, and I'm just going to go straight to the dot cam on this one. You're going to get a problem that looks like this. You're going to have equal charges. Again, you're going to have actually they're going to be different charges, but they're all going to be, they're not even all going to be positive. This is terrible. I'm just terrible. It's going to say like 20 centimeters, 20 centimeters, and 20 centimeters. And they want you to figure out what the potential is right there, what V is right there in the dead center. It's a geometry problem, is what it is. So here's how you do this. Luckily, I was a geometry teacher, and I went, oh, I know how to find the centroid of a triangle, of an equilateral triangle. That's easy. Do y'all know how to find the centroid of an equilateral triangle? Here's what you do. If you drop this angle bisector down here, I drew a bad picture. It's supposed to be 90 degrees. I've bisected that angle. What are these angles of an equilateral triangle? They're all 60. If I bisect it, what does it become? 2 30s. So here's 30. This is 60. This is 90. 30, 60, 90. This bisector comes down. This will be 10 centimeters right here. This will be 10 centimeters. Now then, if I do the same thing, if I go back this way, boom. Now I've got 30, 60, 90 right here, too. Okay? Now, if this is 10 centimeters, this is the hypotenuse, guess what? This is 20 centimeters to right here. All right? No, it isn't. No, it isn't. No, it isn't. No, it isn't. Time out. That is, this is x, and this is 2x. That's right. That's right. This is x, and this is 2x. Oh, my God. All right, let me just finish this right now. In other words, on a right triangle, on a 30, 60, 90 triangle, here we go. Here's 60, 30, 90. On a 30, 60, 90 triangle, if the short end is x, the hypotenuse is 2x, and this end is x times the square root of 3. Okay? That's just the nice properties of a 30, 60, 90. So this distance of 2x is actually equal to 20 over the square root of 3, which comes out to be about 11.5 centimeters. Okay? So whatever the angles are on your thing, whatever the sides are on your homework problem, some of you might have 18, some of you might have 17, something like that. Just go, it'll be the length divided by the square root of 3 that'll be your distance r to figure out, you'll take the potential caused by here, and you'll take kq over r plus kq over r plus kq over r. The hard part on this one is figure out what the heck r was. What's that? No, it's in centimeters. That's why I kept getting it wrong. It's making me mad because I put it in centimeters. You're actually going to see it, and you do need to convert it to meters. You're absolutely right when you start to work on it. Okay, you may go. I'm sorry I kept you a minute over, but we got your 2 hardest homework problems out of the way, so that's good.